This is a lecture on finding the maximum and the minimums and the saddle points for functions of two variables. You can use the same techniques for having functions of three variables and more, but it's very complicated, so it's just restricted in this lecture to two variables, and that's all you have to do in the homework anyway. Let's recall the methods for determining if a point for a function of one variable was a critical point, and if it's a critical point, is it one of the maxima, one of the minima, or is it a point of inflection? And to do that, we used the derivatives. At critical points, the first derivative was either 0 or it failed to exist. So by using the first derivative, we can find the critical points. There's one here, here, up here, and down here as well, at least on this figure. Oh, and there's another one over here. You can see that at all these points, the first derivative is either 0 or it's undefined. Now, to determine if these points are maxima, minima, or points of inflection, we looked at the second derivative. And if the second derivative was negative, as in this case, the point is a local maximum. If the second derivative was positive, then this critical point is a local minimum. If the second derivative is changing sign, going through a 0 here, but changing sign, then it's a point of inflection. See, the second derivative here is less than 0. Over here, the second derivative is greater than 0. Okay, so that's what you have. Maxima, minima, and points of inflection based on the first and second derivatives. This is for a function of one variable. And this is just a summary. For a local maximum, the first derivative is 0, the second derivative is negative. For a local minimum, the first derivative is 0, the second derivative is positive. All right. And at a point of inflection, the first derivative is 0, and the second derivative is changing sign. Now, I'm making an assumption in this lecture that I forgot to state, and that's I'm assuming that all partial derivatives are continuous. So now we'll move to a function of several variables, in particular a function of two variables. In order for a point to be a critical point, either all the first partial derivatives must be 0, or at least one of them must fail to exist. So remember, if you have a function of one variable, you only have one first derivative, and that's either 0 or undefined, failing to exist. But if you have a function of two variables, then you have two first derivatives, the partial with respect to x and the partial with respect to y. Now, at a critical point, either both of these are 0 or one of them fails to exist. Now, if at this point we also have continuous second partial derivatives, then we can use the second derivative test to determine whether this critical point, is a maximum, a minimum, or a saddle point. Sometimes the second derivative test is inconclusive, though. Now remember how many second order derivatives we're going to have. So here we have fxy. We have two first partial derivatives. For the second derivatives, we'll have actually 4. Okay? But because of continuity, these two are going to have the same value. But we are having to do with 4 derivatives. We arrange these in what's called the Hessian matrix. We'll put the derivatives, the second order ones with respect to x here, and the ones with respect to y here. But because of continuity, the off-diagonal elements are the same, and so this really is a symmetric matrix. It's symmetric because by Clairaut's theorem, since the derivatives are continuous, the mixed partials are the same, and so you would have the same value here as you have here. That gives you a symmetric matrix. The second derivative test requires the sign of the second derivative f(x)(x) and the determinant of the Hessian matrix. So the determinant is just called the Hessian without the word matrix, and here's the determinant of it. It is the diagonal terms, the first partial, with respect to x, also with respect to y, minus the mixed partial squared. And this is, we're going to use that plus this in the second derivative test. And here's the second derivative test. First, we determine if that determinant positive or negative or 0. If it's 0, the test is inconclusive. If it's negative, it doesn't matter, nothing else matters. That is a saddle point. If it's positive, then we look at the sign of the the second partial with respect to x. If that's positive, and this is positive, it's a local maximum. If it's negative, and this is positive, it's a local minimum. So this gives you the second order test. And now for an example, we'll investigate the hyperbolic paraboloid. This is a function of two variables, and here's the expression of it. And now I need to take the partial with respect to x, so that will give me 2x over a squared, and take the partial with respect to y, and that's minus 2y over b squared. There's no problem with either of these being undefined, so to find a critical point, the critical point will only occur when this partial with respect to x and the partial with respect to y both equal 0. That only occurs at the origin. Okay, so we're looking at the origin of this hyperbolic paraboloid. And now we need the second order derivatives for the test. So remember, the first one was 2x over a squared. So the second order derivative with respect to x would just be 2 over a squared. And now I have the first partial with respect to y was minus 2y over b squared. So fyy is minus 2 over b squared. And the mixed partials, it doesn't matter what order you take them in because of symmetry, and actually they turn out to be 0 because the derivative of this term with respect to y is 0, the derivative of this term with respect to x is 0, and they're 0. So when I construct the Hessian matrix, I end up with minus 4 over a squared b squared, which is negative. This is a saddle point by the second derivative test. And here's a picture of your hyperbolic paraboloid. We're talking about the point 0, 0 right here at the center of this. Of course, if you had an expression like this, so we say x minus 4 squared over 9 minus y, say minus 9 squared over whatever that was, 4, that's fine. Then the critical point would be at 4 and minus 9, not at 0, 0. Okay, so anyway, we're talking about this point right here. Let me erase some of that. Okay, so we're talking about the point right here, and we said it's a critical point. It's the only point where the first derivatives vanish. It is the only critical point. And by the second derivative test, the second derivative test was less than 0, it was negative. This is a saddle point. You see, if that had been positive, okay, because that's positive as well, you would have had a maximum. I'm sorry, I drew it wrong. You would have a curvature along x looking like this, and you would have the curvature along y looking like that, and that would be a maximum. If it was a minimum, you would have this curvature along x swooping down, and the curvature along y, and that would give you your minimum. But here you've got a saddle point. Look at the curvature along x. That's it's positive. Then look at how the curvature is different when you move along y. That's why you have a saddle point. You've got it falling off along y, but curving up as you go along x, and there's your saddle point.